let's see. Last time I worked with the problem of 13 times 24. This time let's work with something different. Let's work with 11 times 38. Okay, as we write our code, remember that the first line always represents the starting address, where you're going to load this thing in memory. You can experiment a little bit with different addresses if you want. You don't have to use 3000 hex, but it's as good as any. Play with it just a little bit. Now, I'm going to have that 38 stored in memory. Last time, remember, we built it up by doing some things with it. So I'm going to pull it in. I don't know exactly where in memory it is right now, so I'm going to have to come back and fill it in. The actual instruction that I'm going to use is LDI, well, no, just the LD, just the load. The opcode is 2. And then we specify a destination register where we want the thing to go. We've used low-numbered registers. Let's use register 4 just to do something different. Now that's 7 bits. The other 9 bits are an offset. And I can't figure what that offset is until I get the rest of the program written and figure out where I'm going to put that data item. Okay, but at this point, register 4 contains 38. Now, to figure that product, I have to work with powers of 2 to figure out an 11. Well, 11 is 8 plus 2 plus 1. So I will add register 4 to itself. The add instruction is 1. Now, this is 1 times 38. I'm going to put the 2 times 38, let's say, into register 5. But now, remember, these two here are the source registers. This is just fill, those 3 zeros in there. It's going to add the contents of these 2 registers together and put the result in here. Okay, so now register 5 is 2 times 38. And I'm going to do this just a little bit different than I did last time. Right now, I'm going to add that back onto register 4. This says add the contents of register 4 to the contents of register 5. Put it back into register 4. So now register 4 is 3 times 38. I'm going to do that to reduce my register usage a little bit. Now I'm going to double register 5 again. Double that gives me 4 times 38. Do it again. Register 5 is now 8 times 38. And then register 4 is now 8 plus 3, or 11 times 38. Okay, that's all I wanted to do. 0, 0, 1, 0, 0, 1. And there's my trap instruction to halt. Now I can put my data in here. By putting the data after the halt instruction, I'm sure it's not going to attempt to interpret it as an instruction. It won't be executing when it gets down to there. So let's see, 38 is 2 times 16 plus 6. So it's looks like this. Now that I've got that, I can go in and figure the offset that goes up here. Remember, this one doesn't actually show up in the memory. It's used to initialize the thing. So this is at 3,000, and it's 1, 2, 3, 4, 5, 6, 7. So I put a 7 up here, right?
What's the last line? I missed that, I'm sorry.
That's my data.
So that's
38.
38
38.
decimal is 26 in hex. What's my offset?
6.
Remember how those offsets work?
6.
It's a 6. Because it gets added to the address of the next instruction, not the address of the one being executed. So it has to add on to this value to give me the address of the location that I want. So it's a 6, 1, 2, 3, 4. There are 9 bits up there, so that's what the offset looks like. You can't figure that offset until you know where it goes. One of the things to recognize about compilers, anything else, they don't make those kinds of translations in one pass through the data. Because it has to figure out, first of all, you know, how many named variables do you have, and therefore what kind of memory do we need for this, where are we going to put it, how are we going to organize it. Go down and find out where all the instructions are that reference these things. Then you can go in and find out where the data is actually going to go, and you go back and you fill in the address references.
So I do want to explain how we got that offset one more time.
Okay? Basically, the offset, it works this way. The address of the next instruction plus the offset has to equal the address of the data. Because the way the thing works, it takes this offset, it actually does a sign extension so that you get a whole 16 bits out of it. But it takes that offset, adds it to what's in the program counter. The program counter always contains the address of the next instruction. Because the way it works, if you go back and look at all those data paths and all the rest of that, when you load an instruction into the instruction register so that it can be decoded and worked with, as soon as that's done, it increments the PC. And so it's automatically down looking at the next instruction. Is that peculiar to the LC3? Absolutely not. They all work that way. Okay, so the offset, so you figure the offset by taking the address of the data minus what's in the program counter.
So that would be,
In this particular case, my data is at 3007, the program counter is at 3001, and I get a 6.
thank you.
I have a question.
Yeah.
So then how do we know what's in 3007? Is it just our data? Like how do we figure that after we do the haul?
Well, basically, you just have to go through and count instructions. Each instruction occupies one word of memory. You'll begin from whatever your first line in your coding specifies, and then just count them. They go one at a time. All the instructions are exactly one word. That, by the way, is not uniform in all assembly languages. Even the Intel system. Some instructions are longer than others, and it really makes things quite complicated. This is one of the things that makes this one easy to work with. You can figure out where this thing is going to be just simply by counting instructions. See where they are. Does that respond to your question?
Well, I'm still kind of confused because, so we write the halt, but then, like, what is it that we write right after the halt? Like, is it just, like, it just says data, like, I'm just kind of confused. Like, if I were writing a program and I write my instructions and I wrote my halt, and I still have that.
You may not have anything after the halt. We didn't on Wednesday, when I wrote the program to do 13 times 24, I didn't have anything after the halt. Boom, I was done. Because I generated all the data that I was using internally.
Oh, so this is only for when we're like storing the data.
Right. When you're storing some data in memory that you're going to be working with, the best place to put it, not required to, but the best place to put it is after the halt. Why best? Well, do we dare do this? Let me show you what happens. Let's to show you how complex that gets if you don't do it that way. Let's suppose that we want to put our data at the beginning of our program. Well, Okay, here's our data. But if I just do that, the thing is going to set up so that the program counter is here at location 3000, and it's going to try and execute that as an instruction. Ooh. Do we have an opcode 0? Yes, we do. It's a branch instruction. Well, this is a branch instruction. This thing says look at the condition codes. Here's not going to look at any of them. And so the rest of this, 9 bits, yeah, 9 bits out here, is seen as an offset. It's going to change the PC by this amount. It's going to go to, actually it's going to go to 3007. Oh no, it's going to go farther than that. It's going to be 3001, and then we add 26. It's going to branch to 3027, which is probably way out of bounds of the program that you're going to write. And who knows what's going to happen then.
Wouldn't it
So-
increment it by decimal?
Pardon?
Wouldn't it increment it by decimal, not hex?
No, it's hex.
So the 3000s are all hexes?
Yeah, yeah. Addresses are all in hex. Get used to it. Everything that we do in here is in hexadecimal, pretty much. So, the point is that I've got to figure out a way to not encounter that data as an instruction. So, what I'm going to do here actually is insert an instruction before this one. And I'm going to put my data here.
Jump.
At 3001. Now what I've got to put before it, I've got to get around that thing somehow. So I do a branch. Okay, here's our branch instruction. Three zeros here say it's an absolute branch. It's going to do it every time, unconditional. Not less than, greater than, anything else. It's a pure go-to. Okay, now I've got a 9-bit offset. Where do I want to go? Well, I want to actually go down here. This is the actual start of my program. Remember, when it executes this, the program counter is going to contain the address of this thing. I just want to go one beyond that. So that says jump to, as it turns out, 3002. Now, if you got more than one data item up there, you would branch farther, of course. Get around whatever data you've got in there. Just get around them. Okay, now we can do our program. Remember, this is the thing that loads that data into register 4. I'll come back and figure that thing in a minute. 3 was 1, add 4 to a cell, and then add 4. Let's see if I do that right. add register 4 to itself and put the result in register 5. Then we add register 5 onto register 4 and put the result in 4. Then I double 5 twice. And then I add that back onto register 4. And then in my halt. Now let's see. 2, 3, 4, 5, 6, 7. 7, yeah, okay. 0, 0, 6. Okay, now I've still got to figure that offset. What's the offset going to be? Well, remember, we want to take the program counter plus the offset has to be the address of where the data is. When this thing is being executed, the program counter contains 3003. Plus my offset has to equal, the data is at 3001. So my offset now has to be -2. Well, we can figure that. We're working with 9 bits. There's +2. Get -2, I change all the bits and add 1. And that's -2. So my offset looks like this. Notice that sends me backwards, but a negative value in there. That's the importance of the sign extension on the thing. When it changes this to 16 bits, it duplicates this bit so that they'll all be 1s. That preserves the -2. In this case, it duplicated a 0. So you ended up with a positive branch looking ahead. This one looks back. Okay, you see the additional song and dance that you have to do if you put your data in first. You can actually put it anywhere in the program you want and just precede it by a branch that skips over it. But if you don't skip over it, it'll think it's an instruction and execute it. And depending on what the data actually is, you can get some pretty bizarre results going on. Okay, that's why, generally speaking, when you use data like this, it's a good idea to put it at the end. Yeah?
Is data signed or is it the text value at that bed?
The way the data is interpreted depends on your program. You have to interpret it.
The LC3 though, is that it, if it's signed or?
What are you saying?
Like if you add a data line, like at the very bottom at address 307, if you just put if you put 000 then 1111, would that be just at that depth or in hex?
Mm-hmm.
Okay. It wouldn't be signed.
See if I understand what you're saying. If you do this, That's a negative number. But remember that ultimately, all the computer sees are ones and zeros. Now, there are some things that will happen with a negative number. If you notice here on the instruction set, there are 1, 2, 3, 4, 5, 6, 7, 8, 9 of the instructions that have a little plus sign on them. That says that that instruction modifies the condition codes. That's for use with branch instructions. If the result of any operation is a negative number, there is a bit that gets set that says that was a negative number. Okay, so one of the instructions that actually does that is the load instruction. This one right here. If I load a negative number, then it sets that bit to recognize it as a negative number. Now, if in your program you want to work with unsigned integers, cool, just ignore the end bit. This is one of the things you have to recognize about writing in assembly language. It's all up to you and how you choose to look at those bit patterns, how you choose to set the program to do it. Now, some of the internal operations, for example, adding this offset onto the PC, well, you have to remember how that works. Does it really have to recognize this thing as being a negative number? Well, what it actually does, it takes that 3, 0, 0, 3, and adds the offset, 1, 1, 1, 0, and then the rest of them. Because of sign extension, they all turn out to be 1s. Now, it just adds them. There's no thought about, oh, this is a negative number, this is a positive number. No, it just adds them. 1 and 1 is 2. 1 and 1 is 2. Oh, there's a 3. That's 1, 1. There's another 3. 1, 1. 1 and 1 is 2. 1 and 1 is 2. And you see that carry bit just goes off into the bit bucket. So, is it really seeing it as a negative number? Well, sort of. It's just that because of the way the hardware is set up, it just adds the bits. And the way we have designed these things is that it comes out subtracting, and I get 3001 as my address. Okay? Kind of a long way around your question. Does it see it as a negative number? No, not really. It's all how you see it. You can work with unsigned numbers. You can take that number, and then you can take let's see, a short 1, 0 there. You can tell it to add those things together. It'll add them. And carry out of the end of it, let's see. And one goes off into nowhere. Now, as we look at that, we say, oh, 2 negative numbers added together gives me a positive number. That's overflow. Well, maybe. Depends on what you mean by those numbers that you've got in there. Depends on what you mean. You can interpret that result any way you want. It just doesn't. It just doesn't. The two's complement scheme that we have for representing negative numbers, I don't know if he showed you this or not, but there are several other schemes that can be used for representing negative numbers. You can implement them in software and work with them that way if you want. This one just turns out to be easier to work with in the hardware because you don't have to have separate adding and subtracting hardware. You can just use the adding hardware to do both addition and subtraction. That's why it's used. Again, working at this level, when you're right down on the, almost on the gates, everything depends on how you choose to interpret it. Well, let's see. Classic example. If I put in my data here, instead of that number, what does that represent? Well, if I look at it as an integer, it's a 4-1 hexadecimal. 4 times 16 is 64, plus 1 is a 65 decimal. But if I choose to look at it that way, as a character, it's an uppercase A. What does it mean? If I look at it as an instruction, as we were talking about it, it's going to be an unconditional branch to someplace with an offset down in here with those last 9 bits. It's going to jump quite a ways forwards. You see, the same bit pattern can be thought of as a 2's complement signed number. It can be an unsigned integer. That's what you do in all the C-related languages. When you declare a variable to be unsigned, it still just occupies the same bit pattern. It's just how it's looked at within the software. So it can be a signed integer, it can be an unsigned integer, it can be a character, it can be an instruction, it can even be a floating point number if you get down into the thing far enough. All depends on what you're doing when you look at it. Okay, kind of a long way of saying that only in some kind of background ways does the system itself interpret a number as being positive or negative. Particularly with data, it's all up to how you choose to look at it in the instructions that you work with. Well, let's see.
What if you wanted to put a negative number into data? Keep in mind.
At this point, you just need to code it as a negative number. See, if I wanted to put into my data location here, if I wanted to put -2, since I've already converted it, I would have to enter it this way.
So you would just do a sign extension then to fill in all the.
In this case, it's the whole 16 bits. There's no sign extension. I just took this number and did extend it to 16 bits, yeah. But if you want to put a negative number into a memory location to work with, just put it in. But again, at this level, you're going to have to do the conversion. when we get into the next chapter, we'll get to where we can get the system to do the conversion for us, but at this point, you're gonna have to do the conversion. Next time, we'll do something a little more complex. I'm going to go through and find the difference of two numbers, both of which will be stored in memory. We won't phony any of them like we've been doing here. We'll just store two values in memory. We will load them and subtract them, but there's no subtract instruction.